Okay, so today is our sixth session in our this is the water operator training series. And this is our sixth session. So today we're going to go over surface water intake components, well components, and then operation and maintenance for those. And I realize I have the date wrong for you all. That's my date, but you guys are it's the 18th for you all. Um, so and then I am Tucker Colvin. I was the same person who did the one last week or 2 weeks ago, I guess, and a few of the other ones. So it's nice to see you all again. Nice to be back here. And again, we're with the Southwest Environmental Finance Center at the University of New Mexico, in the School of Engineering. And like I mentioned, today's the, what I say, seventh. So this is where we are in our series. And so this is a kind of a bit of a continuation of last week's or the last session where we did 2 weeks ago, where we talked about source water characteristics and just water characteristics in general. And now we're going to go more over the structures, how to take that water and incorporate it into your drinking water systems. Okay, so water sources, this really is the first step in the multiple barrier approach. So where your water is coming from is really the first step where contamination or disease could really occur. So having a safe water source that's well protected from contaminants is really that first barrier in the multiple barrier approach. And I bet some of you probably have heard that term before, the multiple barrier approach. And so this basic concept, you can think of it as Swiss cheese. So there's all these little slices of cheese that have holes in them, and then these holes um, are represent the pathways for contamination. And so all of these different aspects of a water system, whether it's source water treatment, distribution, and then even into pumps and pump facilities and controls, your monitoring and reporting requirements, your data verification, system management and operations, and then operator compliance with the state regulations. So these all represent kind of barriers in delivering water safely to your customers. And the idea is that if one of these fails, so say your source water does get contaminated, then there's another barrier after that, that treatment will hopefully those holes will not line up in a way where the treatment will prevent that contamination from entering the community. So these 8 barriers listed here, these are the 8 aspects of a sanitary survey. And some of them are a little more abstract when it comes to like contamination. We don't really think of system management and operations necessarily with contamination. But the idea with a lot of these is that a well-run system is going to have all of these systems in place, these checks and balances to make sure that there's safe water entering the community and there's people in place that know how to do all this safely. Okay, so this is our first barrier of this multiple barrier approach. So source water, this is what we're going to cover today. Okay, so just to reiterate the types of water sources, this is what we went over last week. So there's surface water. So these are lakes, rivers, streams, could even be canals. Then there's groundwater, and this is accessed with a well or a spring. And then the third one is Gudi or Guidisi, a million different ways to pronounce it. And this is groundwater under the direct influence of surface water. And this is it's accessed in a way and it's similar to groundwater, but it's treated regulatorily as surface water because it has that surface water characteristics and the potential for pathogens. Okay, so water sources, just looking at some of the sources we're going to talk about today. So of course, reservoirs are at the top of these pictures at the top of the slide. It could also be from canals, from streams, and from rivers. And so you'll see a lot of these, even like these reservoirs, of course, they are a pool of water, a body of water, and then the water is taken directly from that pool of water. Um, Canals, of course, this is likely flowing, but it's a big enough pool where there's water that could be drawn directly from there. And then this stream, this is equipped with what's called a diversion dam. So it raises the level of the water. So, and it creates kind of a little, kind of a very small little reservoir almost that allows that water to flow into an intake structure that is just off the side of this picture for in this example. And so these are all in kind of a bit of one category of how you take that water in because it can be taken directly from that surface. Where we'll talk about in a minute, rivers that are kind of lower, they don't have as good of an intake structure, so they can be that water intake can be or what is utilized is called an infiltration gallery. So we'll talk about that in a bit. Okay, so these intake structures that are for some surface waters like reservoirs, like canals and things like that, they have a variety of intake structures. So this is a reservoir and this is a big structure going down, and it's likely that this structure has valves in it, and those valves there's pipes with valves that allow water to flow in from that reservoir into this big structure, this big pillar, and then goes to the treatment operation. There also could be a structure like this that's just along the bank of a stream or a river that has like a grating that's meant to filter out things like leaves and sticks and stuff like that. And then that water flows through that grating and into a pipe. They could also have these structures like this that are these perforated pipes that are underneath the surface. So water flows into these perforated pipes and then through these pipes and then like into this wall and to the treatment plant. And then the valves and the intake structures like in this pillar they could look something like this. This is a big butterfly valve that's like I think 6 feet in diameter that I was actually working on to repair cavitation, but I thought it was interesting. It's just a giant valve that was also very deep down in the middle of a reservoir. Okay, so for reservoirs, of course, reservoirs are filled a lot of times seasonally, depending on where you are in the rainy season or in the Rocky Mountain West because of snowmelt. But drought is also a significant concern. So in these examples, if you look at these towers here, a lot of the intakes are in these towers. And in this one over here, you can see this tower doesn't even look to be in the water at all. So if your intakes are in these towers, even though it looks like there's still some water in the reservoir, the water might not be at the level of these towers, so could have a challenge with that. But a lot of times these towers, they have multiple different intakes depending on the level of the water. So this is just a nice diagram that I think shows this well. Here's our tower with our different levels of intakes in it. So um, these intakes, they are used at different times of the year depending on different things. Of course, changing water levels. So if the water level is lower down, you'll have to switch to a water intake that is lower down that is actually in the water. But there's other issues too. Last week or 2 weeks ago we talked about water quality in a lake and how the water quality changes depending on the depth, and then the sediment and the like minerals can accumulate at the bottom. There's also going to be a difference in temperature depending on from the top of the reservoir to the bottom. And so you may want to switch which intake is used depending on the summer or the winter. And then that will change the water quality. And sometimes with that changed water quality, you'll have to change your treatment methods. So with these different intakes, perhaps you'll do a jar test. And what that really is just figuring out the best treatment methods and the dosage of your treatment chemicals that work best with the different water characteristics. Um, so that's with our reservoirs. So with this, how those intakes work for that tower. And then along a river, these are commonly used. They're called infiltration galleries. And this is one that is being used. This is actually in Billings, where I live. I just took this photo last week or so. And so you can see that there's kind of a bridge going out into the river, and there's this big structure. Then down in the structure is a pipe that has a bunch of perforated pipe that goes underneath the sediment. And you can see the schematic over on this side. So the pipes going down into the river, and then all these pipes radiating out that are perforated, and then the water flows into these perforated pipes. And these perforated pipes are underneath the sediment, and so that sediment acts as a first layer of filtration, actually. So the water that's being taken up that is flowing into these pipes, these perforated pipes, is generally higher quality, a little more filtered than the water in the river, for example. And this is another diagram that I thought kind of shows this well of an infiltration gallery. Just different structure of orientation of how these pipes are set up, but you can just see all these perforated pipes or screened pipes that are underneath the sediment here. The water flows into them, and then they flow through these pipes and are pumped up and then taken to a treatment plant. So that's how these structures work, and these are pretty common throughout this region at least. Okay, so to talk a little bit about the surface water intake maintenance and operations. Of course, we mentioned this before, but keeping that intake below water level, and this is really an issue for not just reservoirs, but also streams. Say that you have like a diversion dam that is creating a a little reservoir for a stream. There needs to be enough water to actually like, keep that full and keep that flowing, and to have that intake accurate or sufficiently taking in water. Um, of course, you have to keep these structures free of debris and sediment. This is a huge challenge with surface water, of course, because surface water has all kinds of stuff that's running off into it, whether it's things like sticks and leaves and stuff, or even just sediment after like seasonal raining, or in the winter here, a lot of the runoff from the snow puts a bunch of sediment into the river. And so, just in this example, this is an infiltration gallery actually underneath this creek. And this is in an area that was recently burned after from a wildfire. And so there's not as much vegetation holding in the sediment. And so regularly all of the sediment flows down and just clogs up this infiltration gallery or the stream above this infiltration gallery. And so water can't sufficiently flow through that sediment into these perforated pipes and flow into the treatment system. And so this system, they have to go in here with a backhoe like all the time and just dig all this out so that they can get sufficient water into their system. Um, and then in this example, this is the same slide we looked at earlier. Of course, this can get all clogged up with leaves and sticks and all kinds of things. This is pretty similar to the plant that I worked at, and we had a bar screen like this that stopped the things that were floating on the surface, but it would get clogged up all the time. So we had this device right behind this screen that was a perforated pipe that was connected to an air compressor. And about once every 15 minutes, a valve was open, and all this compressed air would flow out, and then it would push everything back off of this bar screen, and then because of the current, it would a lot of most of it ideally would then float down the stream. And that would happen about every 15 minutes to try to keep this clear. Of course, we also had to do it manually. We have to take a rake and brooms and scrub this off, and pretty regularly had to manually clean it probably once every week or so. So a lot of maintenance, a lot of upkeep with these structures. And the one I worked at, actually right behind this, we also had a detector for like oil and gasoline, because our stream was right next to a road, and so we wanted to make sure weren't taking in um, any liquids, fluids from vehicles, or even from a boat, because we were below a reservoir. So we wanted to make sure we weren't taking in those volatile organic carbons, those things like gasoline and stuff. So we had a sensor right at the beginning of our intake, and if that sensor detected anything, we'd close the valve for that. Of course, damage from floods is a big concern. I mentioned Billings, where I live. They're repairing this because we had a big flood a couple years ago. and it damaged the structure. And so they actually had to build a temporary bridge out there so they could drive this crane out into the middle of the river. I'm sure it's incredibly expensive to work on this and to build that temporary bridge out into the river. Flooding is a huge concern for structures like this, but really all kinds of structures that are taking in water due to things that flow down the river, like trees, or also because flooding can increase in sediment and plug up our structures as well. And then a lot of times it's in challenging working locations. Um, like in this example, of course, it's in the middle of the Yellowstone River, so a pretty large river, and that's pretty challenging to access. So that's why they had to build this bridge. A lot of times, these valves and or these pipes, intake pipes and valves are underneath, or they're in those towers and those reservoirs, so they're under. I don't know how many, like 100 feet of water. So it's kind of eerie working on this valve to repair the cavitation of this valve, knowing how much water was above me and how deep I was in that reservoir. Um, and absolutely a confined space. So, super confined space working in that location. So a lot of challenges with surface water intakes and maintenance and operations, but or these are the challenges. But with enough training and staff and stuff, they can be adequately maintained. Okay, so that's surface water. Now we're going to move on to groundwater and WDC. So here's just another acronym, but a different acronym for groundwater under the direct influence of surface water. Um, Maybe I even have a typo in there, but my point there is that you're going to see all kinds of different acronyms for that. So just again to go over what we're talking about here. So this is groundwater, so water that's under the ground in an aquifer. And so in this schematic, this diagram right here, you can see the various components of it. So our aquifer right here is labeled number 1 in this teal color. And this can be accessed in multiple different ways. So first way is a traditional well that you have to pump up, put a pump down in the aquifer and send up water through our well. Sometimes these are called artesian wells. And so in those situations, the pressure from a confining layer um, that's created by the pressure in that aquifer that's created by a confining layer actually makes it so when you drill down the well, poke a hole in that aquifer, the water flows up naturally through that well. But a lot of times that flow can be relatively slow. So oftentimes there's a well that, or a pump that's put down this well um, also in order to increase the production of that well. And then the last way is through a spring, and this is where that aquifer comes into contact with the surface so that water can flow out. Um, and those are really convenient because there's no pumping required. And sometimes they can have pretty significant production. Oftentimes they're pretty low production, but really depends on the situation. Okay, so first I'm going to go over those the structures for how to um, utilize springs to get that groundwater. So this is a diagram of a spring box, is what these are called. So over here on our left, in this kind of gray layer right here, is our water-bearing layer. So this is our aquifer, and it is flowing from left to right. And then this spring box has been constructed in this underground, partially underground. So the water is flowing from the aquifer is flowing just directly into this box. And then this box is ideally sealed from the outside, so it is still considered groundwater. And then there's a pipe with that or going into the spring box that that water in that box flows into the pipe and then into the treatment system. So this is the schematic of kind of what these look like, and this is a cross view, and then what these look like in real life, some pictures. Here's what they look like. Some of these pictures are a little close up, but you can kind of get the idea of what these look like. Um, these are the tops of these boxes in this photo and this photo. So you can see that they have these shoebox lids that ideally is keeping out any sort of contaminant. So it can be considered groundwater and it isn't exposed to any sort of outside contaminants such as runoff. This one right here, this one probably would be considered groundwater under the direct influence of surface water, just because it does have that potential contamination. Because you can see that this box, this shoebox lid, is right at about the ground level where there's some runoff that is probably going into this spring box. So in that case, it may be treated as surface water. And these are just kind of the sides of these box with some vents or some access hatches. These don't look completely sealed from the outside, so these may not be totally adequate for sealing that box in and having it considered groundwater still. Here's a photo of one spring box that actually looks more like a small building. And these can actually be, I've seen these as large, pretty significantly large buildings, even depending on the size of the spring. So this is what the view looks like looking into this building. You can see that the spring is flowing up into this building, and but there's also things like roots growing into this. There's a big root right there. And then on this photo on the right, you can see there's like a vent right here, but you can see there's also potentially evidence of water, groundwater, or water, surface water that is becoming coming into contact with this building, maybe even flowing in through this vent. So this is another situation where that spring, which originally probably was considered groundwater, is now regulated as goody because it is has a potential for contamination from surface water. So it would be regulated more strictly. Um, in more of a similar way as surface water. Oh yeah, and the vent is actually an overflow. Thank you, Matt. Matt's the one who took that photo. Okay, here's just another photo of one more spring box. You can see this one over here on the picture on the right. There's a lid here, a hatch, but it's not that tight-fitting shoebox lid, so there could be water potentially flowing into this. It's also growing, or it's also right under a tree that's growing next to it, all kinds of potential sources of contamination, and then some cracks. So could be some contamination in the spring box as well. But if these are constructed well, they can be really convenient because it's very low energy use because the water is flowing. You don't need to pump it up like you would with a well. And then if you can keep it categorized as groundwater, there's pretty minimal treatment requirements depending on the quality of that water, of course. Where I worked in Bozeman, Montana, one of our sources was a spring, and we had a spring box that was well constructed, and so it was protected from the environment, from the outside air and any other surface water. So we got to keep that as groundwater, and the only thing we treated that for was we just added some chlorine, and that was all. So it was really easy way of very simple, pretty minimal maintenance and infrastructure costs and energy costs. So that was a if you have a spring, it can be very convenient. Okay, so now moving on to wells. So this is just a diagram that shows how kind of how wells work. They just are drilled down into an aquifer, and then there's a pump in here that pumps up the water, and then that is then utilized. Again, there's a well that uses like a pump, and then an artesian well. So in this example, this could be under pressure because the groundwater or the water table is higher up than the wellhead, and so the water could come up naturally flowing. Um, of course, a lot of these also have pumps in it though to increase that production, but this is kind of how this would work. These are both aquifers that are unconfined, meaning they are accessed. There's surface access here. So this one, there's a stream that is contributing water into this aquifer. And this one, there's rain falling in this area, and that is recharging this aquifer right here. And then this below this is a confined aquifer. So this is potentially take a lot longer for the water to flow into that aquifer and fill it up, maybe even thousands of years. And it's considered confined because it's not necessarily connected to the surface. So sometimes those are better sources of water, but if they're deeper down, sometimes they have more salts and stuff in them as well. So there's pros and cons of all kinds of different aquifers. Okay, so if we look at our well components here, this is a cross section of a well. And so starting at the top, you can see where like the well head is, where it's above the surface, what you would see. Um, you can see in this green color right here, the pipe that is coming up. And then there's a vent for venting the well that goes into the casing. There's also a sanitary seal that keeps the casing protected from the environment. It is surrounded by a concrete pad, which prevents contamination, and we'll talk more about that in a minute. Here's our water table of one aquifer, and then here's our another aquifer, and this is the one we're utilizing in this example. And so would be considered more of a confined aquifer because it's protected with this clay layer right here. So looking at the well structure, the casing is the bigger pipe that goes down into the hole that is drilled. And then outside of that casing is the grout, the cement grout that forms a seal between that casing and the soil and bedrock and whatever else is on the outside of that. So that protects the the well from contamination, having that seal of grout. And then if we go down here, oh, this is called the drop pipe, and this is the pipe that actually has water that will be flowing up from the pump. Here's our submersible pump. And in this example, the pump and the motor are in the actual well itself. And then here's our drive shoe. So that is just the bottom of that casing. So that just protects the casing from from rocks and things like that. And then the screen. So the screen is a perforated section of the well casing where the water flows in and then is able to be pumped up through that drop pipe and then to the surface where it can be utilized. Okay, so this is just another diagram. You can see the well right here going down. But this in this schematic, this diagram, it shows the water level as the well is pumping. So right here, this level is the water table. So this is the height of the aquifer when the pump is not on or when it's outside of the influence of that pump. But then when water is being pumped up from an aquifer, there's a drawdown. And so the water actually, that water table it actually decreases the depth or it goes down in depth as you get close to that well because the water is being sucked from the aquifer up the straw, up that well. And so the difference between the water table, so the depth of the well where the water would be naturally without the well, and then the water level when the water is pumping is called drawdown. And so static water level is the water table when there's not when it's being not influenced by pumping. And then the pumping water level is the water level when the pump is on. And the difference between those two is called the drawdown. Yeah, think about it. Yeah, static water level. Another name for that, where that water table is. And when you're measuring that, it's measured from the surface. So that the higher the number, the further down the water is. Okay, and here's just another schematic, a diagram of what that looks like. I like this one because it actually shows it as a cone. A cone of depression is what that is actually called because it looks like a cone because it's 3D, as opposed to this one is just, of course, 2D. So that cone of depression is where that water is being sucked down as it's going up through the well. And then in this diagram too, it also labels the zone of influence. So this is the area on the surface where there's potential for like contamination. It's above that cone of depression where that water from the aquifer is flowing into. And so that zone of influence is kind of the area you want to keep um, free of any potential sources of contamination. Okay, so now if we look at the actual well itself, there's a few different kinds of wells and how they are pumped. So this one on the left is called a line shaft turbine pump or an inline uh, turbine pump. And so with this one, the motor is actually on the top and yeah, the motor's on the top and there's a shaft going down and the shaft goes all the way down to the bottom of the well into the aquifer, and that's where the impellers are. And so the impellers are what actually pushes water up the drop pipe and then out this discharge head right here. And so the opposite of that is a submersible turbine pump. So this is when both the motor and the pump, the impellers of that pump, are all down in the well itself. And so in this example, you can see that there's this power cord going down into the well, and that goes to that pump. That is the motor and the pump that's then sending up water through this discharge line. And you can see some other aspects, components of the well in these diagrams. So here's our motor, here's our discharge head. So this is where the water is flowing out after it's pumped up. The column of this motor, and then there's a shaft going down there. The sanitary seal, so this is a seal that it seals the outside from the inside of the well casing, and so it prevents any contamination of that well. Yeah, just support plate for this pump, and then here's our actual well casing that's going to go down into our well. And then if we look at this one on the right, it has similar components. This is a well vent that allows this well to breathe, and I'll talk about more about this in a minute. And there's mesh in here to make sure it doesn't get contaminated by any insects or rodents or anything going up in there, and is downturned to protect it from rain and the elements. This also has a sanitary seal, and then here's our drop pipe that goes down to our submersible pump. Okay, so here's some photos of what those look like. And so this one on the left, you can see that this is the motor up here, and then there's a shaft that goes all the way down into the well and connects to that pump, those impellers that are sending the water up, and then it gets discharged through this pipe and then goes into the ground here and then to a treatment facility. And then this one has a submersible pump. So you can see that there's a power cord going up here and a power box, and then there's the wire going all the way down to the bottom of this well where the motor and pump are both located. And then they are connected to this drop pipe, and then the water flows up through here and then through this plumbing tree, and then for treatment and then to the system. And so if we look at some of the various components in these photos, we'll look at some of these the things that are in both of these photos. So these both have a well vent. So these are important to have so the well can breathe. Excuse me. And so when water is being pumped up, the water or the water the depth in the casing, it goes down, just like I talked about with that cone of depression. So of course, there needs to be air that is able to go into that casing as that water sucks down, and that water gets pulled up through the drop pipe. So the well vent allows water to, or well, the vent air, it allows air to get into that casing. But of course, you want to have that mesh seal and it downturned, so it prevents anything getting into that. And both types of wells, all wells should have a well vent. Of course, there's a power supply for both of these. The one on the left, it is going up to the motor right here. And then this one, like I mentioned, it's going just through this box and then down into the well. And then for this pump, because there's this shaft that is going all the way down the well, there's actually lubricant that is lubricating that shaft as it goes down, um, down the well. And so this is food grade lubricant because of course it could be come in contact with the drinking water. So be sure that there's food grade lubricant that is being used to lubricate that shaft that goes down to those impellers. This pump, this well has an air vacuum relief valve, and so that's this little contraption over here, and this is on that discharge pipe. And this allows air to get in and out of the actual drop pipe where the water is being sucked up. And so with this vertical turbine shaft pump, the it pumps up water from the aquifer, and then when it turns off, because wells turn on and off depending on demand, the water actually flows back down all the way down that drop pipe down into the ground. And so every time it turns back on, it has to bring water all the way back um, up that drop pipe. And so this air vacuum relief valve, it allows air to go into the water, into that pipe and out of that pipe as well. But then there's a ball on it that when water is flowing, it's like a little float. It plugs up the air relief that where it's open to the air, so water doesn't flow in and out of that. Okay, and then in this photo to the left, we can also see a raw water sample tap. So it's important for all wells to have this to take a sample and to get your raw water quality. This is needed to assess the quality of the well water, but also for compliance purposes as well. And then there should be one on this well. Also, it's just not in the photo. So, but I'm sure there is one on the photo on the right too. There's a pressure gauge on this well on the right. So that's important to pay attention to and monitor because the water is being pumped up from this well and is flowing through these pipes at a certain pressure. So you should know what pressure that is at. And then if you notice a change in pressure, it can give you some insight on your pump and if it's pumping properly and maybe if it's going out, you're decreasing your pressure. Yeah, thank you, Matt. And Matt's putting in some notes in the chat, so pay attention to those too. So thanks for adding those specifics, Matt. All right, and there should be a pressure gauge somewhere on this pump as well, but it's probably in the pump house that's not in this photo. Okay, and then this well is equipped with a check valve. And so a check valve is a type of valve that allows water to flow through it in one direction, but not the other way. And I'll talk about more about these in a minute. But the all valve or this well should have one here, and then this well, it probably has ones further on in the system. Doesn't have one in our photo. But of course, we don't have check valves going down the drop pipe because that water flows back down it. And then a flow meter. This is similar to a meter that goes to houses. It just totalizes the amount of water that's flowing through the pipe. Yeah, thank you, Matt. Yeah, photo on left has a check valve in the vault to the left of it. Oh, right of it. Thank you, Matt. And there's also a flow meter for this for the well on the left too, just in a different location. Okay, so both of these examples that we looked at, the water is flowing up through the well, the head of the well and up into the surface. And so you can see where the water is flowing in both of these pictures, right here in this one, and then up through the well in this picture. But in a pitless adapter, these operate a little bit differently just because that pipe doesn't go all the way through the top of the well. And so these are called pitless adapters because back in the day, wells used to be in a pit, and so that's where all the different um, components of the well were and where it was accessed. And so there was concern of contamination because all that stuff was in a pit. And so these were developed to have that water not flow up through the wellhead that was in a pit and then instead flow out through the side of that well casing while it's still underground. And so this is the schematic of what these look like. This is as it's going in. And then as it goes in, this is how it's situated. And so you can see it's connected to the wellhead through this rope. There's also the power cord that's going through here, but then the water is going through this pipe and then out this discharge pipe. And this is still underground. And then it's going to a facility. And so this is what that looks like. This is the wellhead. So this is what it looks like above ground. And so you can see that this is where the power cord is going up through this cap and then is going down into the well to power that submerged pump that's located in the well. There's a vent. This is what that is right here. And so that allows the well to breathe. But as the water is being pumped up, it doesn't come up through the surface. It goes underground. And then in this example, this is where it pops out. This is actually, well, ironically, this is also in a pit. But this is where all of the appurtenances and the equipment along this plumbing tree are located. Yeah, thank you, May. Oh, yeah, yeah. And freezing and cold climates, probably not a problem for you all, but where I live in Montana, definitely a concern. So it's nice to have all of this underground, prevent flooding or prevent freezing. I mean, excuse me. Okay, so this is what it looks like after that discharge pipe goes out of that casing and then it goes through the ground. This one is actually in a pit, mostly underground, but this could be in a building above ground as well. And now while we're looking at this, I think this is a really nice photo that shows all the different components of a well as it's coming up out of the ground. And so if we go from left to right, the left side is where the well is flowing from. And so the water is going from left to right through all these different contraptions. So if you go through and look at what all these all are, this is a check valve. So this allows water to flow in one direction. We talked about this earlier. But just to look at this a little closer, this is an example of how this looks like or of what this looks like. There's all kinds of different contraptions of how these work, but this is a pretty basic one. The water flows up and it can flow this way, but then if it tries to go the other way, there's a spring that closes that valves, and so it doesn't allow water to flow down. And in a well that actually has a submersible pump, these are actually throughout the drop pipe as well, and so that prevents the water from flowing back down into the well. And so in this picture, there's all these different check valves throughout this pipe, and then as it gets to the surface as well. And then there's one at the bottom that's called the foot valve, and that is the lowest down check valve. So that prevents contamination from the water going the opposite direction. Okay, there's also a raw water sample tap right here. We talked about this a bit earlier. Pressure gauge, and so that shows the pressure of the water as it's flowing through this pipe. And if this is connected to a pump or to a tank, excuse me, this pressure gauge can also give you some insight on the level of that tank as well, because water creates pressure, and gives you and this could tell you how much water you have in that tank. Okay, and then these next two things are a flow switch and the chlorine injection. And this is more about treatment, so I'm not going to talk about this a whole lot now. But just so you know, that's what that is. And this is chlorine, liquid sodium hypochlorite that's being injected into this pipe here. Here's our flow meter. So that's important to know how much water is flowing through your well, and that has a totalizer on it. And then while we're talking about flow measurement, in this picture, this is a meter similar to what you'd see for a house. But there's different kinds of flow meters. If you're measuring surface water, sometimes there's V-notch weirs. And so in these two examples, you can see the water is flowing through this little notch right here. And so the depth of how far down this weir the water is flowing, you can translate that into a flow in like gallons per minute or cubic feet per second. And similar concept of a partial flume. So this is a rectangular structure. It's not as much of a drop like the V-notch weir is, but the water does drop down a bit and it increases velocity. And then you can measure the level of water in this flume, and that will tell you, you can translate that to the flow, how much water is flowing through that flume. And so these are used a lot in surface water. You can see even here, though, it's in a facility at a water plant. But they're used for all sorts of things, even irrigation ditches and such. And then there's flow measurement inside the pipe. So there's mechanical flow meters, and there's a whole variety of different kind of apparatuses that measure the flow as it goes through that pipe. And then there's a non-mechanical option, so pressure differential, also known as Venturi flow meters. And then there's magnetic flow meters and ultrasonic flow meters, and these are just ways of measuring it that doesn't have a moving thing in the pipe. And I won't talk about these too much now, but no, there's a whole variety of different kinds of flow meters. The next component we'll talk about is this air relief valve. So in this example, this is a bit similar to the one I talked about earlier on that other well, but in this example, this only allows air to release from the system. It doesn't allow air to get sucked into this pipe. And these are important because all wells and distribution systems, they need to breathe because there's always dissolved gases, dissolved oxygen in the water. And so that can escape and it create air bubbles that get trapped in the system. So it's important to give them a, opportunity to leave the pipe through an air relief valve. Also, if this water is flowing directly to a storage tank, that also would let the air release from that pipe too. And then the last thing in this photo is isolation valve. So it's of course important to be able to isolate this well from the rest of the distribution system for maintenance or if this is ever taken offline or anything like that. Other well components that are not in that last photo. Um, oh yeah, thanks, Matt. A treated water tap. You're right. Yeah. So because this system, it only is for the only treatment is chlorination. So this would be raw water tap right here. And then it looks like right there is a treated water tap. Okay, so then in this photo, this is just another well. There's a well inside this building, and then here's our plumbing tree right here. This is a blow off for that well, and that's important if you ever need to flush a well for any reason, in case it gets contaminated with something. You want to be able to turn on that pump and pump out that water and send it somewhere other than the treatment plant or the distribution system. Um, a lot of wells are equipped with a pressure transducer. So, of course, water creates pressure from its weight. And so this pressure transducer, it can tell you the pressure of that water in the well, and that will tell you the that static water level and then that pumping water level. And then you can know your drawdown as well from when you turn your pump on. And it's really important to know what this is because you want to make sure your pump is in the water. If you're in an area experiencing drought, perhaps that water table is dropping down, and it's possible that your pump may no longer even be in your aquifer. So it's an important thing to measure. Or if it could be in that aquifer, but then when you turn it on, the drawdown could be so much that it sucks air. And of course, you don't want that. Wells, the electrical components and the mechanical components should be protected with surge protectors. And then this one has a surge can, and so this is a protector from like lightning. There could also be, or I've also seen facilities where have like a lightning rod on the pump house and then it's grounded. And so that protects it from surges from lightning. But this just protects your equipment and out protects outages after like a lightning event. And then, of course, there needs to be some sort of controls for your well pump. And so that could be as simple as having just a timer for your well to turn on and off for a certain number of hours a day. It could be connected to a float in your tank that when your tank gets below a certain level, it could just turn on that pump and fill it up. Or it could be something all the way up to PLCs, programmable logical controllers, could be connected to a SCADA system. It could really go from very simple to more advanced. In these examples, these are just photos of some control panels. You can just see some of the aspects of it. This one on the left, you can see things like tank level, how much amps are being used by the wells. by those pumps, how much flow there is at that moment. This is for two different wells. There's these sub monitors that monitor like voltage, and they're similar to this motor saver over here. So you can monitor how much electricity your pumps are using, and that can also tell you, give you some insight on how, if your pumps are starting to fail. There's also things like totalizers, with how many hours those pumps have ran, different indicators for if it's on, if it's off, if there's an alarm, different controls, so hand, on, off, auto, the number of starts for that pump. So um, it really depends on your pump and your controls, what all of this has, but um, a lot of these things can be really helpful. There should definitely be some sort of alarm. So if your pump fails to start, it should trigger some sort of alarm. Something maybe that's just like a light outside of the pump house. Sometimes it can be connected to SCADA and it can like call you on a phone if that occurs. But it's so important to have some sort of alarm for a pump if it doesn't turn on. And then lastly, backup power. So of course, depending on your system, you could have one pump or one well, or you could have a whole bunch of them. But it's important to have backup power for those wells if power goes out, because of course you want to keep your community supplied with water during a power outage. Or if there's just a power outage for just your facility, you want to be able to have backup options. So this one has a generator, look like a trailer that you could pull in. Sometimes they're actually built into the facility, but it looks like this one probably just has a hookup for like a rental generator that can be used when needed. Okay, so just to talk about well operation and maintenance. Um, The most basic operation maintenance you should is just have a log sheet for your well. You should have these for just all sorts of different facilities at any kind of plant. This is just a basic example over here that has the date, time, meter reading, the pressure, the elapsed hours for that well, if it's on when you're there, and then who it was. You can have all kinds of other columns for various things depending on what your facility, what kind of other things you have, like maybe amperage or things like that. Um, and it's important to keep these logs so you can note any changes. Also, any water quality changes you should see. If you ever see those, you should note that as well, and that can give you some insight on what's happening with your well or your aquifer. And then thinking about the actual well components, you should analyze these on occasion, relatively regularly, to make sure they are all in good working order. There's, of course, wells components that are above ground and below ground. And so a lot of these, you're not going to be able to analyze them or evaluate them very regularly. Things like your sanitary seal, depending on where it's located, maybe you can see if it's intact still. Your depth of your casing, depth of grout, your depth of your pump, the screen interval, those are all things that you should be aware of what they are. Um, they're not going to change much. Your static water level and your drawdown, we talked about those, and it's important to analyze those and record those so you can see if there's ever any changes in your water table, whether it's going up or down. And then above ground, things like your well casing, make sure it's in good shape, that concrete pad, your sanitary survey, if you can see it, or sanitary seal, excuse me. Make sure the well vent is working properly, electrical supply, check valve, pressure gauge, etc. All those things we went over. And so just to look at some of these things, these are just the wall components, make sure they are all in good shape. In this facility, it's looking pretty good. The one thing that we noted is that this air relief valve, this should be plumbed up above the surface because in case of this well pit floods, there's potential for contamination for that flood water to get through into this air relief valve and then into the system. So that's something that should be changed in this photo, but other than that, it's looking pretty good. So thinking about wells, it's important to think about location, where that well is located. Is it area subject to flooding? Is it in a depression at the bottom of a hill? Is it in a pit? And that pit could flood. Here's just a photo. This one looks like it's probably in a pretty good location. Just going through a few examples of not wells that are not in good location. Here's one that's a flooded pit. There's also openings into the well. So that's pretty big source of contamination. This one just looks like it's an area where there's a lot of flooding. These wells are in depressions, and so kind of the water collects in those areas and then could contaminate that well. Here's just one where it looks like it's in a depression where some little creature built a home. These ones, of course, contamination could be contamination from these cattle right by this well. This one's in a parking lot, potential contamination from vehicles. This one right in the gas station, of course, contamination from the gas station from people filling up their vehicles, but also there's probably underground storage tanks for the um, for the gasoline and diesel, probably right next to this well. Also, it's also in a pit, so not great. This one looks probably okay, except there's a bunch of herbicides that was used for the vegetation around here, which could be a contaminant for the well. So yeah, don't watch spread for spreading herbicides by your facilities. And then there's one, that one looks pretty good. Sanitary seals, make sure those are in place. There's no openings into your wells. This one just doesn't even have a well cap at all. And this one has like bolt holes, it looks like, that are um, not sealed up. Well vent, make sure there is one. It's at least 18 inches above the ground or 3 feet above maximum flood level. And make sure that it's pointed downward and that it's screened. Here's this photo of missing well vent. And then in these ones, with a well vent like that, there's a screen up in this little cap thingy. And then there's one that's attached with a hose clamp. Casing, it should be at least 18 inches above the ground and protected from flooding. And then should be well capped, protected from any sort of contamination from flooding or animals and such. These ones are just too low down, could be prone to flooding. Concrete pad, you should analyze that. There should be a concrete pad that has a 3-foot radius that is sloped away from the well, so water flows away from it. And then why is it important to have a concrete pad? Because a well, it drills down into the ground and it creates a pathway for contamination just right next to that well. So by having a concrete pad up here, it prevents those contaminants from getting into all these cracks next to the well and contaminating the aquifer. So here's just a bad example of, yeah, no pad. Here's a nice pad, 3 feet on each side of the well. Here's one that's just kind of being eroded away. That one just missing a concrete pad. And then electrical supply, all electrical components should be in a conduit and in electrical boxes. Just potential here for loss of electrical control, or it's just protected, or it's not protected from the elements. This one is just a wire that's going into this hole. So not only is the cord protected, it also is a pathway for contamination. So here's just what some good ones would look like. Okay, and then lastly, site security. Every component of a water system should be protected from people that could want to break in and do anything to your water system. So there should be a fence with barbed wire, razor wire on top, and then there should be signs like this: warning, tampering with this facility is a federal offense, so keep people out of there. This one, just no fence, no security, just right next to this road. This one has a fence, but it's pretty easily could just crawl under there. There's a good example at the end. And then remember to lock your gate. Okay, so we're just about at time. So that's the end of our presentation for today. And so we'll be back in 2 weeks. And in 2 weeks, we'll start our disinfection series. We have a few different ones on disinfection. And first, we're going to talk about chloramines, UV, chlorine dioxide, and chlorine disinfection. So that's it for today. So we'll see you all in 2 weeks. I think Matt's doing the one in 2 weeks.